work that I did during my master's degree, which was basically an evaluation of how the stress invariants and the hardening conditions that might impact the plastic flow behavior of metallic materials under monotonic and cyclic conditions. And the main interest on this topic is based on the fact that for many applications we're interested on knowing what's going to happen with our structure beforehand, and to do so we need to run numerical simulations, which will of course depend on a given choice of a constitutive model. For instance, we want to know if our material will fail on a ductile fracture or fatigue, which are phenomena that usually or more often happen in the presence of plastic flow. But the quality of our predictions, it's highly dependent on the choice of the constitutive model that we are using. Meaning that if we choose poorly, we might end up with unpleasant results, and this was a particular interesting case, which was some oil leakage in the Gulf of Mexico, which was associated with the malfunctioning of this valve here, and several reports afterwards suggested that the valve did not work due to improper use of a Mises-based model. My point with this is to show that we need to properly choose the constitutive models of our numerical simulations. And to do so, we need to ask ourselves what are the loading conditions that we want to consider, what are the hardening of the material by experience, the material itself, if we have a new criteria in mind. And for many years now, the most used approach are the so-called von Mises or J2 based models. And the key ingredient here is that no matter the stresses that you're looking at, all of them they will yield on the same value of equivalent stress, which is a function of J2. But it so happens that for many materials, J2 alone is not enough to describe the plastic flow behavior of some metallic alloys. We see that the loading conditions might impact the plastic flow, all the relevant stress invariants, namely I1 and J3, which are the two aspects that I will focus on this work. But we also see that the environment might also impact the plastic flow of this behavior, these materials. From the yield surface perspective, what we observe for these alloys is that neither Trask or Mises surface describe properly the yield surface of such materials, and to do the yield surface of such materials are actually located in this blue region squeezed between the two yield surfaces. And to do so, we need to account for more relevant stress invariants, namely I1 and J3. In this regard, the main objective of this work is to analyze the impact of I1 and J3 on the plastic flow behavior of the metallic materials, covering monotonic, ultra-low cycle, and low cycle conditions. And to do so, we use the 1045 steel alloy as a model material, and we propose a Gauss-based model with mixed hardening to describe the behavior of such alloy, and we show what are the advantages of doing so. So the key ingredients of the model we propose are first the Gauss equivalent stress, which is basically a generalization of Mises stress to account for the effects of I1 and J3. The former being controlled by parameter A, while the latter by parameter B. And differently from what you will see in traditional plasticity theory and some works in the literature, we assume that the flow vector might have a volumetric component, meaning that it's not necessarily a deviatoric tensor. And finally, by mixed hardening, I mean that the model is built in a way that in the most general case, it can account for both isotropic or kinematic hardening. But it's also possible to run the model with a single type of hardening. So, moving to the monotonic loading conditions, we extracted the data from tests performed by bverified specimens, which are a nice geometry because with a single specimen you can generate several stress states by simply varying the loading direction. We implemented this in an academic, per se, finite element code called HiPlus. Here we only consider isotropic hardening because it's a common approach in monotonic cases, and also we didn't see great advantages on coupling kinematic hardening in these conditions. We calibrated the isotropic parameters using data from a standard tensile test, and the values of A and B were calibrated via a trial and error procedure. And here are the results in monotonic tension. And first, we see here that if we do a J2 analysis, we don't get the correct force displacement curve that you would observe experimentally. And the model we propose generates a much better agreement with the experimental reaction curves you would see. Another interesting thing is that here we notice that to properly describe the reaction curves, we need to activate the effects of I1, and if we don't do so, we don't get a significant correction in the low displacement curves. More importantly, we see that I1 in these conditions is the strongest parameter. On the other hand, when we move to the monotonic shear case, we see that once again, von Mises' approach does not describe properly the reaction curves you would observe experimentally. And here, J3 is the key parameter playing in the plastic flow of this material. And these trends we also observe for the combined load cases, which are basically when tension and shear happening in the same place. And I'll be happy to show to you if you want by the end of the presentation. With these results, we decided now to simulate the ultra-low cycle fatigue conditions. And here, since we have we basically did the same procedure that we did for the monotonic case, except from the part that since you have load reverses, you need to account for kinematic hardening, which of course needed a calibration of the kinematic parameters. And the values of A and B that we obtained for the monotonic case, we use here for the ultra-low condition. And by doing so, here are the low displacement curves you will get. We see once again that von Mises does not provide a good response that we would observe experimentally. But on the other hand, our model does not provide either satisfactory results. This indicates that the values of A and B that we use here are not proper for these conditions. And more importantly, this suggests to us that perhaps the hardening conditions that we're considering, they also impact on how I1 and J3 will influence your plastic flow. And we see this in this case, and also in a reverse shear case. Based on this, we decided to recalibrate these parameters, and by doing so, we were able to generate much better agreement with the experiments, both in the compression tension case and the reverse shear condition, which confirmed for our suspicions that indeed the hardening conditions are impacting on how I1 and J3 will influence the plastic flow of this material. Now we move to the low cycle case. Here we extracted the data from this very nice report generated by Lise and Saucy, who performed many fatigue tests on smooth cylindrical specimens. Here we only consider kinematic hardening, which required another calibration of the kinematic parameters. And here we did what I call a Gauss point level simulation, which is basically it would be the same thing if you would simulate a single file element. And here are the yield surfaces you would get if you calibrate your Mises model in fully reversed uniaxial conditions or in fully reversed shear conditions, showing that this material is at least J3 dependent. And I'm pointing out this because one of the limitations of doing the simplified simulation method it's because I cannot capture properly with this the effects of I1. So here we limited ourselves to only analyze the impacts of J3. And since all the models, they coincide uniaxial conditions, I'm only going to show the results for fully reverse shear loading. And here are the hysteresis loops you will get. We see from both models, and we see that there are some differences on the loops, although not as pronounced as we've seen before for the two previous cases. And for fatigue life assessment purposes, we are very interested sometimes, especially if you're using critical plane methods, on stress amplitudes. And here's a comparison between the amplitudes you would get from both models compared to the experimental ones, and we see that our model agrees better with the experiments, although both models have considerable high deviations for high shear strength amplitudes. But I would like to point out here that for critical plane point of view, the differences between the two models are not significant in the sense that you will probably not get enhancements on the fatigue life assessments you would get by using critical plane methods. On the other hand, when we see the evolution of the accumulated plastic strain predicted by both models, we see that the evolution rate of this variable is different in both cases. And I believe that if you use an incremental approach, such as continuum damage mechanics, for instance, to predict fatigue life, you will get considerable fatigue life differences. So I would say that using a stress invariant sensitive model could be very interesting coupled with a damage model. With this, we show that this material is indeed, in all the loading conditions that we studied, I1 and J3 dependent, meaning that to properly describe the behavior of this alloy, you need to account for this stress invariance. We also see that I1 and J3, the way they impact plastic flow is also influenced by the hardening conditions you're considering. And I personally believe that incremental methods could be possibly benefited from using such a model that accounts for this invariance in the analysis. With that, I would like to acknowledge the Brazilian Research Council for funding this work, and also the Jesus College in Oxford for letting me be in this conference. Thank you very much.
Thank you very much for your presentation. Any question is displayed on the screen? Yes?
Yeah, I assume when you do the modeling of the butterfly specimen, use for measure specificity, you somehow have a tensile test on which you fit the hardening law.
Yes.
Is that correct?
Yes.
Because that was some kind of implicit in your talk.
Yes, it's because it was a very extensive presentation, and I was afraid that I wouldn't have time to. But what I did, we calibrated indeed our.
We still have time.
Oh, I'm glad to hear that. But yeah, we did that. We calibrated our model using an inverse approach, using a standard tensile test. So it's not only curve fitting. There is a whole optimization procedure going on here.
I find that the difference between the butterfly simulation and the actual experiment is huge.
Yeah, it is. And some people might think that it's because if you calibrate the model, von Mises model, in that conditions, you would get a good result. But the thing is, if you move to this condition and try to generate the reaction curves you would see, and a standard smooth cylindrical space, you'll probably not get the same result. That's why Mises is a bit limited in this sense.
Okay for you?
Maybe one more.
Yeah. Go ahead.
Did you check that the material is isotropic? Because your criteria is assumes isotropic behavior.
Yes, it is. It is implicit assumption. I personally did not check, but the works that I extracted the data, they said that it was fairly isotropic. But I would say that I'm not sure, to be honest.
Okay.
I believe what they said, yeah. But I didn't personally do the task and etc. to verify that.
Okay, any other question? Or everybody wants to have a coffee? I guess everybody wants a coffee, but just before that, let's thank again our speaker.